In the past, you learned to calculate derivative. The game was, I give you a function, you give me its derivative. In this specific case, the answer would have been that. Today we'll be playing the game backwards. I give you the derivative, let's say 2x, and you need to find which function it comes from. In that case, f of x is equal to x squared is a possible answer. We have seen that a quantity grows or decays exponentially with time if it satisfies this equation. Note that this equation involves the derivative of your function. This equation, which involves a derivative, have a special name. They're called differential equation. Well, equation because it's an equal sign, and differential comes from taking the derivative, means there's a derivative function involved. And whenever you do some mathematical modeling, be it in biology, in finance, in physics, in chemistry, you will see differential equations everywhere, because these will describe how something changes. So let's look at the easiest possible type of differential equations. These are the ones where you are given the derivative and you need to find the function. So to solve this, we need to do the opposite, the reverse of differentiation. We want to go backwards. We want to find a function that differentiates to 3x squared plus 2x. And such a function is called an antiderivative. Anti because we're going backwards, obviously. Sometimes these functions are also called primitive. So an antiderivative or primitive of a function f is a function whose derivative is f. Let's try that on an example. We want to find an antiderivative of 3x squared plus 2x plus 1. What that means is that we want to find a function whose derivative is 3x squared plus 2x plus 1. Can you find one? Can you find more than one? Maybe you want to pause the video and try? So the first answer most people will have, they will recognize 3x squared as being the derivative of x cubed, 2x as being the derivative of x squared, and 1 as being the derivative of x. So clearly, this one works. Now when you get the question, is it possible to get another one, another function which would work? Well, you would need to have this. But maybe if you want to add whatever, let's say 7, then when you take the derivative, you're going to get that again. And you added 7, but there was no special reason to add 7. You could have added any number you like. You could have added pi, minus 13, whatever. So indeed there is more than one. There's an infinite number of them, in fact. Just add any constant you like. This example shows that finding the derivative of a function and finding the antiderivative of a function are quite different. From one function, you get exactly one derivative. But now if what you know is the derivative and you want to go back, there is some uncertainty. There are several functions which work, right? It depends on the constant you add in the end. For that reason, instead of trying to find the function that has been used to generate the derivative, we decide to find all the antiderivative at once. And we decide to give the set of all the antiderivatives of a given function a name. So we call it indefinite integral. It's indefinite in the sense you can't really know what function it is, it's a set. There is a symbol for that. This part looks like an S, and we'll see later on that it comes from a sum. The dx here, for now, just reminds you that the variable of interest is x. So if you want to find all the antiderivatives of a given function f, here is the method. You need to find one of them, just one, which I call capital F down there. And once you have this one, you can get all the others by adding a constant to that one. Using symbols, that means the set of all antiderivatives of f is obtained by finding one particular antiderivative means one function whose derivative is little f, and then adding a plus c. Let's apply this method on an example. We want to find all the function whose derivative is 3. So if we remember that the derivative of 3x is 3, well, we found one. We did this step. And then to get all of them, we add the plus c. At this point, some of you probably wonder what the plus c is, what it's there for. Well, it turns out that 3x is a function whose derivative is 3. But so is 3x plus 27, because the derivative of the constant 27 is 0. And that's not the only one. 3x plus pi also has a derivative equal to 3. So there's an infinite number of functions that differentiate to give 3. And 3x plus some constant describes all of them. So if we were to play that game again, well, I'll tell you, okay, I thought of a function. The derivative is 3. Can you guess what my function was? You shouldn't answer, I think your function was 3x plus 4, because it's very easy for me to answer. No, it was 3x minus 32. What you should answer is, your function is of the form 3x plus some constant. And that way you win, because this describes all the possible functions I could have thought of. This explains the word indefinite in indefinite integral. If you start from the derivative and you try to get the function back, you don't get one specific function. You get an infinite number of them. You actually get one for each possible value of the constant. In that sense, the answer you're giving is not really well defined. Let's apply those concepts on example. If you feel confident enough, don't hesitate to pause the video and give a try to the exercises. The first question asks us to check if capital F is an antiderivative of little f. That's a vocabulary question. So we need to check that if we take the derivative of capital F, we indeed get that. So let's take the derivative. We notice that in capital F there is this 1 on x cubed, so it probably would be a good idea to rewrite it differently. So we can use this formula that says if you differentiate something that looks like x to the n, you get n times x to the n minus 1. And that works for all values of n, positive, negative, integer, fractional, anything. So let's first rewrite f. We can then differentiate with respect to x. We get a constant in terms of function, so keep the constant multiplied by the derivative of the function using the rule above, and then we use the same rule again for the second term. The negative 3 drops at the front, I decrease the exponent by 1, and the derivative of 5x is 5 times the derivative of x, which is 1, and I'm getting 21x to the power of 6 minus 3 on x to the 4th plus 5, which is indeed little f. I recognize it there. And that's the definition of antiderivative. Part B. Another good time to pause the video, I would say. This time we want to find all the antiderivatives of this function. We've seen in the previous slide that in order to find all the antiderivatives, you need to find one function which differentiates to f of x. In other words, you need to find one antiderivative, and then you get all of them by adding a constant. So it turns out that we know one antiderivative. It's been given to us. So that's our capital F, and then to get all the others, we just add a constant. Let's try the other examples. Here we recognize this formula where n is 17. So we're trying to find one antiderivative. If we start with x to the 17 and differentiate, we're getting this back. Now we need to find something that's going to differentiate to give negative 31. Negative 31 times x will work. Now I can't stop there because that would be one antiderivative and I want all of them. And I know that all of them will be of this form plus a constant. This time I need to dig in my memory. For the derivative formula. I know exactly which function differentiates to give exponential. It's exponential itself. And then in order to get all the antiderivatives, I add a constant. Last one, we just said that exponential is its own derivative. So if I differentiate 7 times exponential, I'm going to get 7 times exponential. And a function which differentiates to give 5 is 5x. And I add a plus c to describe all the antiderivatives. The previous example showed that one way of finding antiderivative is just to use the derivative formulas backwards. For example, the first question asks, find all the function whose derivative is equal to cosine x. So we try to think of the derivative formulas we know, and we know that sine x has a derivative equal to cosine x. Therefore, we find one this way, and then we add the plus c. So really, the formula we have already memorized is this one, and we use it backwards. If you give me the derivative, I can tell you the function was sine x, plus a constant. You may want to pause the video now and start practicing using your derivative formulas backwards. See you in a second. So let's do this one now. If the derivative is equal to sine, well, we don't really have a function like that because the derivative of cosine is negative sine. So if you add a negative sign here, you're going to get a minus, and a minus, that's a plus. A function whose derivative is exponential, we know that. Exponential is its own derivative. And don't forget the plus c. Sequence squared, that should ring a bell. That's the derivative of tangent. 1 on 1 plus x squared is the derivative of inverse tan. Yes. And 1 on x is the derivative of logarithm of absolute value of x. If you want all the derivatives, you add the plus c. The reason for the absolute value is that 1 on x is defined for every real number except 0. So we found an antiderivative for it, which is defined for all numbers except 0. And that wouldn't be the case if you took logarithm of x. If the derivative is x to the n, the function was... well, you'll have to find out. We're going to be investigating. I'm not giving you this one, just left a blank so you can add it onto your slides. Let's try. Again, it's probably a good idea for you to pause the video. We do not have in our list of derivative formulas a function whose derivative is x. But we have a function whose derivative is 2x, that's x squared. Now, if instead of 2x we want 1x, what we could do is divide by 2. And therefore the derivative will be 2x on 2. So we found one antiderivative, we just need to add c. For those of you who are a little confused, please note that x squared on 2 is the same as 1/2 times x squared. In other words, it's a constant times a function. And when you take the derivative, you're going to get the constant, the 1/2, times the derivative of the function. So when you differentiate this, what you will get is 1/2 times 2x, and that's indeed x. Let's try to do something similar for the next one. We don't know a function whose derivative is x squared, but we know a function which has an x squared in its derivative, that's x cubed. So when we take the derivative, the exponent will drop down at the front, so we will get 3x squared. And for the same reason, we divide by 3, so the 3's will cancel. And we add a plus c, because remember, this symbol means you want all the antiderivatives, not just one. What about x cubed? Well, if we want to get an x cubed, what we have in mind is this function that says, if you take the derivative of x to a certain power, the exponent drops at the front, and the index goes down by 1. So if after going down by 1 the index is 3, it means that before that the index was 4. So we know we're going to need x to the 4th. Now when you take the derivative with respect to x of x to the 4th, you're going to get 4x cubed. And you don't want the 4, so what you could just do is multiply by the constant equal to 1/4. And that tells you that x to the fourth on 4 will be one antiderivative. And now, to describe all of them, just say that they're the antiderivative you found plus a constant. By now, the pattern becomes visible. If you have a 2, you get a 3 here and a 3 in the denominator. When you have a 3, the exponent is 4 and you divide by 4. So if your exponent is 17, you will do the same thing. Increase the exponent by 1 and you get 18 and divide by the same thing. And of course you could check if you differentiate with respect to x to the power of 18 on 18, you will get the constant 1 over 18, and then you multiply by the derivative of the function. And you get what you wanted. Now, if we look at all these examples, we can see a pattern. Every time we have increased the exponent by 1, and then we copied in the denominator this new exponent, and then we added c. So we can use all the example in the first column to see a pattern and therefore guess a formula. Let's now look at the examples in the second column. There are the one where the exponent is negative, and we're just going to see that this formula we just found actually also works for negative exponents. For the first one, though, you may not need it because it's very likely that you recognize this derivative. You know a function whose derivative is almost 1 on x squared because the derivative of 1 on x is minus 1 on x squared. It's almost the one you want. And you know that if you just multiply by the constant negative 1, then you will get the derivative you want. Therefore, you found one function whose derivative is 1 on x squared, and you find all of them by adding c. Of course, if you didn't recognize this derivative, it's not a problem. Just rewrite this as x to the negative 2 and apply this formula just like we will do in the examples below. So in question B, this negative 3 here is the n there. So the formula says just increase the exponent by 1. So if you increase the exponent by 1, this is what you get, and divide by the same thing. I'm writing all the details since it's the first time. So you get x to the negative 2 over negative 2 plus c. And you can check by taking the derivative. Question C, same thing. Increase the exponent by 1 and divide by this exponent you just found, and then add c to get all the possible antiderivatives. We now have this formula that gives antiderivatives for powers of x. Let's use it on some example. I think it's a good time for you to pause the video and try it for yourself. Question A, n is equal to 2. The formula says increase the exponent by 1, divide by the same exponent, and add c. In the second one, we have a constant times a function, and we know that in this case, we just keep the constant and we can multiply by the antiderivative of the function, which, according to the formula above, is just obtained by increasing the exponent by 1 and dividing by this exponent. Usually this is written by putting all the numbers at the front, so it would look like this. Same thing with this one. It's exactly the formula above with n equal to negative 5. The formula says decrease the exponent by 1, divide by the same exponent, and add c. Yes, increasing by 1 means moving 1 unit to the right, so you get negative 4, not negative 6. This one, constant times function. Keep the constant, find an antiderivative for the function, and the formula says that your n, increase the exponent by 1 and divide by this same exponent, and then add c. Okay, so in that case, it's directly the formula. We get x to the negative 8 plus c. Question E is one of these cases where it's just easier to first rewrite the function before finding its antiderivatives. So let's rewrite it using the index laws, and then we're ready to use our formula. Decrease the exponent by 1 and divide by the exponent you just found. we will be using the same idea for question F. It's a good idea to rewrite using index laws because the formula we have is in terms of indices. The rule says increase the exponent by 1 and divide by this new exponent you just found and add c, and that's really x to the power of, so that's really a half plus 1, 1.5. And then the easiest way to deal with things like this is to multiply the top and the bottom by 2. So I'm going to get a 2 at the top, and at the bottom, when I expand, I'm going to get 1 plus 2. That's a 3. And I shouldn't forget to add c. Another way of getting this is doing the famous skip me, change me, flip me. Question G, same thing again, probably a good idea to rewrite the function first. So x is x to the power of 1, the square root is the power 1/2. So really we have x to the power 3/2 here. We use our rule again, increase the exponent by 1 and divide by this exponent. And again, I'm going to use my trick I love so much. I'm going to multiply the top and the bottom by 2. And then that gives me 2x to the power 5 squared. Here I get a 5 plus constant. In this video, we found antiderivatives by using our derivative formulas backwards. There is really something missing here. Remember when we were calculating derivatives, something we were using also which is not there is the chain rule. So we will have to learn how to find antiderivatives when the function we get is a derivative that's been obtained by the chain rule. The way to do this is called substitution, and we'll do this in another video. So thank you for watching this video on antiderivatives.